Okay, so these are the four main properties, or the three main properties of this quantum bias busting algorithm. There is a fourth property, which is that this algorithm is practically utterly useless. It's practically useless. So I'll put a little ironic happy face here. Why is this useless? I mean, if you don't think about it too carefully, this sounds pretty good. Like, let's assume that, like, you actually care about this biasness property, that you're, like, mildly interested in this task of, like, I give you some and or not code, like, hey, is the truth table, like, biased or unbiased? It sounds pretty good. Like, here we have, like, this kind of probabilistic statistical test. It never gives you any false positives, and it sometimes gives you true positives. Sounds great, right? Like, awesome, I've got this test that does it, and it's efficient. But it actually practically has like no good guarantees at all. Perhaps you can suggest why? Like, it might do something good for you, but it also might not. This sum here is like a real weasel word. Sum. Because this sum might literally be like 1 in 2 to the 1,000. So I'm like, okay, strictly speaking, that's positive. But like, if some good event happens with probability 1 in 2,000, 2 to the power of 1,000. If I'm like, let's have a prize pantry drawing, the probability of success will be 1 in 2 to the power of 1,000. That will never happen. That will literally never happen in our lifetime, in the lifetime of the universe. 2 to the 1,000 is such an enormous number. It's useless. So like this, guarantee is like saying like, oh, sometimes I'll actually positively tell you that like I'll positively bust this bias function, but like that could be like a 1 in 2 to the 1,000 chance. And then from a practical point of view, it's useless. So let me just say that a little bit more precisely, that this probability could be exponentially small. So for example, suppose perhaps this Boolean function you're maybe trying to bust, let's say it has 1,000 input bits and 1 output bit. Perhaps its truth table has 2 to the 999 plus 1 zeros and 2 to the 999 minus 1 ones. Right? That makes sense. The sum of these two numbers is 2 times 2 to the 999, which is 2 to the 1,000. So it's like, if it was 2 to the 999 zeros and 2 to the 999 ones, like that would be unbiased. But this one is like, is very, very slightly biased. Then what is the average of the plus or minus 1 notation truth table values? Well, I guess we get 2 to the 999 plus 1 copies of plus 1. And we get 2 to the 999 minus 1 copies of minus 1 divided by 2 to the 1,000. So let's see. This cancels. We get plus 1 and get another plus 1. We get 2 over 2 to the 1,000. Okay, which is 1 over 2 to the 999. So this is saying, like, if this is your f and you do this whole like rigmarole up to here, you finish the Hadamard transform, and the final amplitude on 0, 0, 0, 0, 0, 0, 1,000 zeros, will be this, 1 over 2 to the 999, which strictly speaking is not 0, but it's, super tiny. And therefore, the probability that extract all outputs all zeros is the square of this, which is 1 over 2 to the 1,998. And this, by our definition, this is like the probability that the overall algorithm outputs biased. Okay? So while it is true that like the algorithm kind of works, like this is a biased function, and there is some chance that the algorithm will be like, busted, you're biased. That chance is 1 over 2 to the 1998. Okay? And so from the point of view of like, if you're actually trying to learn if f is biased or not, you run this, and it's like no comment. And you like run this again, it's like no comment, no comment, no comment. You'll say no comment till the age of the universe, probably, because it only has like a 1 in 2 to the 1998 chance of actually saying biased. Any questions about this? So now you realize, man, this whole quantum computing thing is like really disappointing. Like, you know, this is one of the coolest quantum computing algorithms we know. Yeah. Yeah, the question is, is there anything we could learn from the amplitudes of the other basic states? Kind of. The amplitude of the other states will not give us any helpful information about whether or not f is biased or unbiased. So if our goal in life is to try to understand if f is biased or unbiased, looking at the other amplitudes won't help, as it turns out. Now, looking at the other amplitudes might help you, or you can't look at them, but like maybe analyzing them and extracting all and seeing what you can infer if the extract all output was something else, like 0, 1, 0, 1, 0, 1, 0, 1. But it does teach you something about the function f, something that's like even like more complicated than like its biasness. But we will get into exactly that next time. Okay, so right, so why might we still be interested in this algorithm despite the fact that like in practice it's useless? So we would never actually use this to like make our lives better. There is some reason, and it's to do with the following question. Here's a question for you to ponder. Could there be any classical probabilistic algorithm with properties 1, 2, and 3? Okay, these were like the good properties of the quantum algorithm. Could there be a classical algorithm that also has those properties? So let's see. Put yourself, this is a question about classical computing. You don't need to know anything about quantum computing for this. Imagine you're like in 210 or, I don't know, some like basic course, and they're like, try to do this. Try to write some code, and you can use randomness in your code. Try to write some code whose input is some and or not code. A little bit weird, but okay. And your code should try to detect if the truth table is biased. And you can use randomness, so you can like try to do some statistical methods to detect it. And the three things are, you have to have like a write an efficient code that, you know, is at most like 1 million steps. I mean, you can't take exponential time. So one thing you could do, if you were allowed to take exponential time, is you could be like, I will take this code, I will literally compute the whole truth table, and then I'll count up the number of zeros and ones. And if it's exactly a 50-50 split, then I will output biased, and I'm perfect. You can, of course, do this, but that's an exponential time algorithm. So that's ruled out by number 3. So you could say, like, OK, I could just say no comment for every possible input, but like that's also like not allowed. So I can't do that. So you're like, OK, I have to come up with some algorithm that like has some chance of outputting bias when it really is biased. And it's also allowed to have no false positives. And that's like really strict. Like absolutely no false positives. So it's really hard to imagine what you're going to do. Like you got this like code with like 10,000 instructions in it, this and or not code. You're like, I don't know. Like one thing I can think about doing is I will pick a random 1,000-bit input, and then I'll run it through the code, and I'll find out what the output was, 0 or 1. That's kind of like saying I will figure out one row in the truth table. And you can do that. You can, I don't know, figure out the first 10 rows in the truth table or the first 1 million rows in the truth table. You can figure out like a bunch of random rows in the truth table. You'd be like, I'm going to pick a bunch of random inputs, find out what the output is, and I'll get like a bunch of random rows in the truth table. But like, you're still stuck, right? Like, imagine you do that. You pick 1 million inputs. You compute the and or not code on all of them, and you get like all the outputs. Imagine all the outputs were 1. You might be like, that is crazy. Like, all the outputs are 1? Like, this function f is probably unbiased, or is probably biased. But you could not like say like, in that circumstance, I will output biased, because it could be a false positive. There could be like some terrible chance that you just happen to get like 1 million ones, even though the truth table was unbiased. It could happen. So I'm trying to intuitively convince you that it doesn't seem possible to do this task with the classical algorithm. it really does not seem possible to have a classical probabilistic algorithm that achieves properties 1, 2, and 3, which then you're like, oh, that would be kind of cool, because then we'd have a quantum algorithm that can achieve this 1, 2, and 3. So like I would really have demonstrated quantum is better than classical at something, at least one thing. Now that something is like a practically useless thing, but at least I would like kind of get some evidence that like, hey, quantum computing is like a real thing. It has like the power to do something that classical computer cannot do. And there's kind of like a cool fact, which is like here we spent like 1 minute thinking about this question, where it's like, I don't know, it doesn't seem like classical computers can do it. But kind of impressively, computational complexity researchers, people like myself, thought about literally exactly this question in around like 1990. Like 33 years ago. And this was like before this quantum algorithm came out. It was before like 99.9% of people had even heard of quantum computing. For some crazy reason, like these researchers thought about this exact question. Could you have a classical probabilistic algorithm for this task with properties 1, 2, and 3? They thought about it. It's kind of amazing. It's the power of basic research. And one such computational complexity researcher called Mitsunori Ogihara in 1990 proved a theorem that says no such algorithm exists assuming P does not equal NP. Actually, there's a slight asterisk here, which I'll mention. And that's awesome. So like everybody believes that P does not equal NP. If there's one thing that like we know in life, despite the fact that we can't prove it, but if there's one thing we really know in life, it's that P does not equal NP. Come on. And so, to the extent that we believe this, we equally well believe that there's no classical algorithm solving this task. And that's cool, because then that's like true evidence that quantum can do something, even if it's kind of practically pointless. Quantum can do something that like classical algorithms simply cannot do. And later in the course, we'll try to finally do something that with quantum computers that classical algorithms can't seem to do that's also not useless. But for now, this is what we have. And let me just say, it's like technically not this. It's like some higher dimensional analog, like NP to the NP does not equal co-NP to the NP. If you want to find out exactly what this means, you should take undergraduate complexity theory 455. Otherwise, let me just say, it's extremely similar to P does not equal NP, and to the extent that we believe P does not equal NP, we equally well believe this. Okay, so next time we'll find out about all the amplitudes after you do Hadamard transform.